Yeah, so I decided the key word here is a school. This first week is a school. So you're all here to learn something, and hopefully learn something new. And my one aim today is that everyone should learn at least one new thing. And of course, you're a very diverse audience, so some of you are going to be interested in what I'm going to say, some of you won't be. But it is so elementary that I think it will interest all of you if you're interested in multiphase flows. One of the things I could have done is dazzle you with some recent research, and I'm kind of going to do that, but only at the end, and only after I've done all the schooling. Okay? So one thing that is a hot topic at the moment is kind of drag reduction using structured surfaces. Super hydrophobic surfaces you might have heard of, or liquid infused surfaces. Hands up if you've heard of liquid infused surfaces, and don't be shy. There's a strong bias on this side of the room. Well, you know what? Just as a background then, let me do what all of our students do, and you look it up on Wikipedia, and here's what it says. They've got different names. Liquid impregnated surface. A slippery, liquid-infused porous surface, liquid impregnated surface, or liquid-infused surface, is a multiphase, there's the key word. A multiphase surface consists of two distinct layers. The first is highly textured, or porous substrate with features spaced sufficiently close to stably contain the second layer, which is an impregnating liquid that fills in the spaces between the features. Okay, the liquid must have surface energy well matched to the substrate in order to form a stable film. Notice they keep emphasizing the word stable there. And I think, Demetrius, I'm going to leave, you can talk about stability issues. This afternoon you're going to hear about stability issues, but I'm going to keep it much more basic. This is the geometry I want you to have in mind throughout this morning's lectures anyway. So these are grooves. I can only point at one screen. So these are grooves or features in the substrate, and we're imagining they're longitudinal grooves. So the flow is going into the board or out of the board along the grooves. Okay. But maybe you've got an upper wall, and of course this is your substrate. So these are patterned features in the substrate, and the key point is, this is where the multi-phase aspect comes in. You want to drive a fluid through the channel, and we're thinking kind of microfluidic applications. Very low Reynolds numbers, so very viscous fluids. It takes very high pressures to pass those through. One thing you'd like to do is lubricate so that the pressure gradients you need to force this working fluid through are less. Okay? And one way you can do that is by filling these grooves with a second fluid, a lubricant. Okay? That's why they call it liquid infused surfaces. Okay? And of course, the blue there is, I'm going to imagine a fluid, for purposes of today's school, I don't want to say lectures, some fluid of one viscosity and then a working fluid of another viscosity. Okay? And of course, here comes the complication. There's an interface between the two fluids. Okay? So this is the kind of multi-phase aspect of it. And this is a paper that only appeared less than 6 months ago, look. And what we did in this paper, these are my two students. We found some analytical formulas to describe drag reduction in these surfaces. And then this paper tests them numerically to see how good those asymptotic formulas are. And what we show in this paper is that actually these analytical formulas are completely explicit. They do very well across a large range of geometries of those surfaces. Okay. Now, I'm not going to go through the paper. I'm going to go through all the little bits that kind of make up the paper so that if you want to go and read the paper after today's lectures, you'll understand it much more. Okay? Everyone happy with that? That's next. All right. And by the way, please ask questions, because it's only when you ask questions that I know if you're following me. I'm going to try and stand, but it's a long time, so I might have to sit down eventually. So let's, I'm going to try and be neat as well, but I might also be quite fast, because I want to get through this. Let's imagine we've got an upper wall. Yep. The what? Oh, you can't see. Shall I do landscape? Let me do landscape. Okay, let's imagine a simpler situation. We've got no liquid infused surface yet. Well, we've got an upper wall, and let's imagine we're taking a cross-section here of a channel. This is liquid. And I've got an upper and a lower wall. And suppose this is at y equals h, and y equals minus h, and maybe of course, y equals 0 is there. And it's a single fluid, viscosity mu. And maybe I could drive it with a pressure gradient, but I won't. I'm going to do Couette flow. So maybe let's insist that this plate is being driven into the board with some speed. Let's call it U plus. And then this one's, I can let that move as well if I want, or it could be stationary, U minus. So I've got kind of shearing this fluid. And it's a single fluid. So this is a single fluid case. And let's write down the Navier-Stokes equations. Anybody not heard of the Navier-Stokes equations? Steady, that's the steady Navier-Stokes equations for the U, which in general will have three Cartesian components. We use Cartesian coordinates, U, V, W. But let's assume we just got unidirectional flow into the board. Steady, okay? And so in other words, this is kind of X, this is Y, and that's Z coming into and out of the board. Okay? Everyone happy? There's my single dynamic fluid viscosity for this single fluid. Okay? So there's no pressure gradient. Here, I'm assuming it's driven by these Couette forcing. You're moving the top plate, say. So what happens to this PDE when I assume this unidirectional steady flow with no pressure gradient? Well, what happens to this? Zero. But it's still Navier-Stokes. I haven't cancelled it out by some zero Reynolds number assumption. It's just not there in this case. What about this one? That's not really there either because I'm just assuming a Couette flow, right? And so what I actually end up with is just this, and I don't even need the viscosity here. Del squared W, where del squared is just the two-dimensional Laplacian. Okay? So I've ended up in a situation, not like you see in an viscid fluid mechanics course. This is a viscous flow, but I've got unidirectional flow with no pressure gradient, so I've got Laplace's equation. It's a harmonic velocity profile. Everyone happy? Okay. My U plus and U minus, I'm assuming, don't vary with X. They're just constant velocities. They're just plates that are moving into the board. So actually, I'm expecting unidirectional flow. That's what I expect, because there's no inhomogeneity in X. Okay? So actually, I'm loving this, because all I end up with is this. Unidirectional and no X dependence in the forcing. Who can tell me what the integral of this is? Huh?
Straight line.
Straight line. Let's call it AY plus B. A and B are constants, of course. In fact, let's impose the boundary conditions. W at H. WH is U plus, W at minus H is U minus. So actually, I think I'm not going to spend too much time on this. You can see, right, that if you just fix A and B using these, you just get that plus this. Actually, I think I missed an H out there. Oh, no, there isn't an H there, no. My notes are correct. Okay, that's the solution. Okay, that's the Couette flow between two plates of a single fluid. One of the things you might be interested in is suppose the bottom fluids, let's suppose that U minus is 0, so the bottom plate isn't moving, I'm just shearing with the top plate. You might ask what the shear stress is at the top plate. Okay, the shear stress, well, of course, is where the viscosity will come in, is going to be this, dW by dy evaluated at y is equal to h. That's the shear stress at the top plate. So, you know, that's kind of the amount of stress you're going to need to drive this flow. Can we see what that is? Well, there's the solution. You just take the derivative, evaluate at y. What you get is mu u plus over 2h. Okay. Everyone happy? All right. Let's go straight to multiphase, but in the simplest way we can imagine. Two-phase. So what I'm going to do now is I'm going to have top fluid of viscosity mu plus and a minus fluid with viscosity mu minus. Okay, and this is also going to be this is a wall, of course. Well, let's think about what you might expect to happen. Okay, I've got equal layers now of mu plus and mu minus. And imagine that mu minus is lower than mu plus. What do you think is going to happen in terms of the shear stress required to generate the flow in this case? If mu minus is less viscous than this one, you'd expect the stress needed to drive the flow to be less, because it's like a lubricant layer. Let's find the flow. So what you have to do is you have to solve the PDE piecewise in each layer. So you've now got a W plus and you've got a W minus. Those are the flows into the board in each layer with obvious notation, W plus, W minus. Well, W plus, look, is going to be U plus, let's call it some shear rate. I don't know what that is yet. Y minus H. Everyone happy? I've satisfied the boundary condition. Look at Y is equal to H. And this is going to solve this. And then W minus will be U minus plus W minus, some other shear rate, Y plus H. Everyone happy? So I've satisfied my boundary conditions at the top and the bottom, but I don't know gamma plus, the shear rate, or that shear rate. How do I find them? Anybody?
Continuity.
What's that?
Continuity.
Continuity. You see, here's an interface. By the way, if you're let's just go back to this first phase. Have you heard of the word Dirichlet? Well, look, this is basically, I've got del squared W with W given on the boundary of the domain. That's known as the classical Dirichlet problem. Okay. Now, I've still got Dirichlet conditions on the top and bottom, but in the middle of this interface, and that's what this whole course is about. Well, of course, the whole thing is about multi-phase flows across interfaces. What conditions do I have at this interface? Let's discuss this for a little bit, because it's quite a pivotal. How many conditions do I have? He says 2. Anybody disagree? What are they, by the way?
Continuity of velocities.
Yes.
And continuity of stresses.
Yes, but that last one, how many is that?
How many is, here is 2.
Yes. Remember, this is where you have to just be careful, especially with Demetrius coming up next. Look, I've taken it to be a flat interface. But it's an interface, so it can generally move. And I've assumed it's flat, and what I'm doing there is I'm assuming there's some kind of surface tension, I guess, keeping it flat. Okay. because I might expect, for example, a Laplace-Young balance. The pressure jump across it must be given by the curvature times the surface tension. So if the curvature is 0, then I've got continuity of pressure. That's a normal stress balance, but then I do want a shear stress balance as well. So that's probably what you were thinking of when you said 2, right?
Yes, yes.
Yeah. Given that it's flat and I've disregarded the pressure condition, a normal stress balance, remember that Dimitri's isn't going to ignore that because that's where the waves are going to come in. I'm ignoring that, but I do want continuity of shear stress and I do want continuity of velocity. Let's hope that's enough. Well, I need W plus equal to W minus at y equals 0. What does that imply? Oh, minus. Correct me if I make any mistakes. And then I need continuity of shear stress. Now the shear stress we already know because I worked it out in the last problem at the top boundary, but now I need this to be true. I need the two shear stresses in the two components to balance at y is equal to 0. So you can see, look, if I take these, that means that mu plus gamma plus is mu minus gamma minus. Or I'm going to write that, everybody, like this. I'm going to use this sigma. Am I still on the board? That's going to be this non-dimensional viscosity contrast. Okay? So look, these kind of strain rates at the interface are not the same. I've made the velocity change. Of course, now I just have to do a solve. And I'm not going to do that. Everyone can solve these. So let's solve. You get that gamma minus plus is u plus minus u minus over 2h. No, over h, not 2. Not 2. It's sigma plus 1. And then this is sigma. Okay? So notice there's this sigma rescaling. Sigma plus 1 rescaling. So let's work out now the shear stress at the top. Oh, let's keep this up. Let's keep this up. So the shear stress at the top wall, and let's choose this, is mu plus dw plus by dy evaluated at y is equal to h now, and that's just mu plus sigma plus dot, which if you just work it all out based on this, it's sigma mu plus over sigma plus 1 u plus over h. And you know what, I'm just going to substitute back for sigma. So that's my shear stress at the top wall. What's the first thing to check?
Do you get the same solution last time?
Very good. See, he's going to be my favorite person. Okay. Okay, when mu minus is the same as mu plus, I should retrieve the single phase case, where I know that this is the answer. Oops. Do I? That gives me mu plus squared over 2 mu plus. Gives me mu plus over 2. Good. But what happens, look, when... Notice there's a multiplicative mu minus there. So if mu minus is significantly less than mu plus, I get an advantage, right? In the sense that my shear stress at the top wall has gone down. That's the kind of lubrication at work. And in fact, you see, if mu minus is very much smaller than mu plus, this is quite a dramatic reduction. By the way, there's an analogy here. Does anybody recognize this formula? This expression? The product of two viscosities over the sum? From A level? Baccalaureate? Would you ever do conductors in series and parallel? I know there's a couple of GTAs from my course. Yeah. So if I've got a conductor, two conductors in series, the resistances add, right? So the conductance, let's call it plus. That's basically conductance scales with, this is H, this is H. Conductance is a conductivity. This is like a conductivity scalar, and this is the height. So C minus will be C minus conductivity over H, and the resistance is, what should we call them? R plus is going to be 1 over C plus, and R minus is 1 over C minus. Remember, conductance is 1 over the resistance, and resistance is add in series. So the effective resistance is R plus plus R minus. Remember that from A level? Well, that's 1 over C plus 1 over C minus, which is H over C plus hat plus H over C minus hat. If you put it all over common denominator, you get exactly what I just wrote down. When I invert that, sorry, I got it the other way around, right? When I invert it, because I want the effective conductance, well, there should be an H on the bottom. I'm doing this quickly because this is just an incidental comment. But basically, the viscosities here are acting like, so the mathematical problem is exactly the same as passing a current through two different conductors in series. Okay. That was just a side comment. Okay. Let's move on to a slightly different situation. Now, notice in this, I should learn from my lecturing that I should keep all my... Now, the thing is, I've got an infinite interface here, and Demetrius, I'm sure, is going to tell you about the stability things. If you've got one fluid shearing over another, it's not a particularly, unless you sort things out carefully, it's not going to be a particularly stable situation. So, or you might not expect it to be stable. So what I'm going to do is, I'm going to introduce a little grating. I want to make the menisci a bit smaller and have them pinned at certain places. So let's add a grating to enhance stability. Okay, so I've still got my upper wall, I've still got my lower wall, but now look, I'm going to have a bunch of plates, solid plates, with the menisci, but not menisci, they're the interfaces. Periodic. Right, and I assume it goes. I'm going to add a grating. This is for stability. I want to make the menisci, the interfaces less, pinned at the edges of these, this grating, if you like, but then still contact between the fluids. So I've still got plus and minus fluids. What do you think about that? Let's look at the boundary conditions again. I've still got W is equal to U plus here. I've still got W is equal to U minus there, say. I've added a grating. That's going to increase the friction, isn't it? Because these are going to be no slip surfaces on all of these little slats. Imagine slats, okay? But I've still got contact between the two fluids across this periodic array of interfaces. Okay? So I'm going to have the same boundary conditions now at the interfaces as I had in the two-phase problem. So here's a note. This is an example of what people call a mixed. It's not Dirichlet, it's not Neumann, it's kind of like a mixture of the two, but it's not even just Dirichlet and Neumann. I've got Dirichlet with continuity type conditions. So it's not even a standard boundary value problem, mixed boundary value problem. But it is a mixed boundary value problem. Not particularly standard because of the multi-phase nature. Okay? A classical mixed boundary value problem is where you give me Dirichlet and Neumann on different parts of the boundary. That's typically what people mean by Dirichlet and Neumann. But I haven't quite got that. I've got Dirichlet, but here I've got continuity conditions between two phases. Okay. What happens here? The edge of one of these slats. So look, this is the edge of the slat, but to the left of it, I've got no slip, and then to the right of it, to the right of it, I've got no slip, and to the left of it, I've got those interface conditions. People call that, we can call that a triple contact point. Okay. Triple contact point. So I've got no slip neighboring with an interface. Okay. So there exists triple contact points. That's another thing to bear in mind. Here's something you may not know. Whenever you've got a triple contact point, you've got to expect singularities of some kind, a priori. It may be that it's very nice and you don't have any, but you must expect them in advance. So here's one thing that I'd like you all to learn, because I think this is always something you should do, no matter whether you're doing something computationally, CFD, whatever, Basilisk or OpenFOAM. You must know what the problem is doing locally. I mean, if you're discretizing or putting a mesh, you've got to know if you need to put more mesh points somewhere. And it's kind of obvious that these are going to be delicate points. You've got these no-slip mixing with an interfacial conditions. Moreover, the more information I have about those triple contact points in terms of the nature of the singularity will be crucial for accuracy in any numerical method. You've got to know what's going on. Okay? Otherwise, you're shooting in the dark. Okay? Just one other thing. I know Dimitri's probably talked a lot more about asymptotics than I will, but let's suppose H, that's the height that this upper and lower wall is away from this grating. Let's suppose that this is 2L, say, that's the period of the grating, and I don't know, let's call this 2C. Let's suppose that H is much higher than the period, 2L. So let's suppose that H is much, much larger than L. So you've got this grating, but the walls that are driving the flow are kind of far away. What might you think to do if you wanted to get a bit of analytical control? Well, I'm thinking to myself, if that's the case, my interface, the problem is kind of going to look like this, except my interface is a heterogeneous thing. It's got some holes in it. You know, it's got interface, but there's also some no-slip bits. But because the wall is still driving the flow, for most of the flow, it's going to be the same unidirectional flow. Except when I get close to y equals 0, close to the grating, I'm expecting it to need some more resolution, because I need to somehow incorporate those no-slip boundaries as well. Okay? So I'm thinking that there's going to be a separation of scales here. So basically, I think there's going to be some kind of boundary layer. It's not the standard use of the word, but there's some boundary layer near y equals 0 where I'm going to have to resolve all of these slats. But outside, up and down, away from the boundary layer, I'm expecting it to be unidirectional flow with some effective shear rate. Oh, there it is. Okay. Everyone happy with this idea? that if my wall isn't, if my driving wall isn't too close to my slats, I can separate the scales. It's a little inner boundary layer with an outer unidirectional flow that I've already solved for. Okay. Think of yourself in the little layer now. Suppose you're in the little layer near y equals 0. What are you going to feel from the outer coet flows? Huh?
Shear.
Yes, with some shear rate. But you know what? I'm thinking to myself, in the little layer, you need to tell me what the shear rate is, because that's what's going to move me. But you better tell me, that's going to be an input for me. Okay? So, you see this, now that I've introduced the grating and these triple contact points, I'm a bit worried I'm going to be able to do anything analytically. But let's use this asymptotic, I call this the high wall asymptotics. Okay, it allows me to do an inner-outer separation in Y. Okay? Unidirectional flow, like I've just solved for, and then this little layer, this boundary layer. I want to make things even simpler. Because I'm still worried about my inner problem. My inner problem at the moment, in this little boundary layer, is going to be an infinite array of slots with some interfaces, with shear at top and bottom. I've got to solve that. That's still a bit too hard at the moment. Anybody think of some other asymptotics I could do to simplify things? Let me just write that down. Look, my inner problem is basically this problem. And then I've got W tends to Y far away. Maybe, I don't even know what this is. Some other one, some other shear rate. So this is my inner problem. I've still got a periodic row of slats with interfaces with far field shear both upper and lower. No, it's this one. I'm giving you clues with everything I write.
Periodic.
It's periodic already.
So we can solve it for just one cell.
Using what asymptotic parameter is going to be small for that to be allowable for me?
C. 2C.
2C, but that's not non-dimensional. 2C divided by is
2L.
2L, well done, you see? When I scare you enough, you come up with the right answer. I need my interfaces to be well separated from each other, because then they don't really, if I have an interface, I don't even see my neighbours.
I have a question.
Yes.
It's just the drag coming off the back of one of the interfaces. Surely that would affect the other one. Or does that come into play?
This one and this one?
What domain, does it include two of the
No, this
slats?
is an infinite array of them. So there's an
But when you make it periodic,
oh no,
when you just consider a
very good. Thank you for your question. Yes. So this would be a typical period window, say.
Oh, okay. So
Yeah. So there's one interface per period, and there's
but you still have
two
both
edges of the slot.
Yeah.
Okay.
Yeah.
There's still only one slot. By the way, don't forget when you do periodic problems, your choice of period window is up to you.
But I get my question, but you couldn't. You have to kind of include. You couldn't have this. Just having one of the solid slacks in what you.
Yes, I could. Yes, I could. I'm going to draw it more carefully. How many periods do you want? Is that enough?
No, but if you just had one,
Yeah.
how would you know the effect of the boundary of the other one? Like if you had an aeroplane.
By enforcing periodicity. That helps it communicate the fact there's others.
Okay.
Yes, thank you for your question. I'm glad you're thinking intuitively. Yeah, the point is if I enforce periodicity, that means that there's others. That's making me periodic. That's coming in through the periodicity requirement. Now look, I could pick my period window here. Then I've got one interface and one slot, except it's in two halves. Or I could put my period window there, and then I've got one no-slip solid and two halves of the same meniscus. They're the same by periodicity. Okay? Any other questions? Of course, remember, what's forcing the flow here is the shear. So he just came up with it there. He's saying, so what I'm going to assume, look, is that if this is 2C, I'm assuming that 2L is much smaller than 1. So in other words, this is what I call the diluteness asymptotics. By the way, that's just the word that seems to permeate the scientific community. It's just when two things are far away from each other, you call it dilute. Okay. So can you see what I'm doing here? I'm using height asymptotics to produce an outer inner with an inner boundary layer, and then even the inner problem is too difficult. I'm going to use diluteness asymptotics. There's separation of these interfaces in the layer. Everyone happy? And of course, I'm going to expect both of those to break down in two different ways. They can both break down separately. Either I could start getting non-dilute, in other words, my neighboring interfaces are getting closer and closer, or the upper wall is getting closer to my boundary layer. And then I've lost the asymptotics. But I'm hoping that the asymptotic results I get, having made those assumptions, will still be quite accurate. Because it would sure be nice if I didn't have to do the full numerical simulations. Okay. Even with one interface, I've still got my triple contact points. So let's look at, do you know what? I'm going to do a local analysis. And by the way, this is something I notice people just don't do. You read papers, people don't do it. They just don't do it. Or they waffle. They waffle about it. So I'm going to do it because I think this is probably the most important thing you're going to learn from me. Look what I've drawn. I've drawn one contact point. Here's an upper fluid. Here's a lower fluid. Let's put it at the origin. Why not? Where else would I put it? I've got del squared W plus is 0. And I've got W equals 0 on there. That's my no slip. And then this is the interface. Everybody with me? I would like to know what W plus and W minus look like when Z is small, meaning when I'm close to the triple contact point. Oh, sorry. Well, how many, okay, hands up. How many people have not done a course in complex analysis? You haven't? Don't worry, it's not going to be that difficult. Basically, everything you did, all the algebra you did when for real analysis just is the same, except there's much more powerful results. What I'm going to do, here's a fact, I'm going to introduce complex potentials. Yeah, I heard some exclamations of surprise. And I know why. I know why, because everybody thinks complex potentials are just for inviscid fluid mechanics. But who told you that? I'm going to introduce what did you say? H plus of Z. What's Z, my friends? It's X plus IY, where I is the square root of minus 1. What's he doing? Now, the reason I'm introducing H plus just as a function of Z, and notice there's no Z bar in there. By the way, that's what I mean by an analytic function, a complex potential. It means that this function does not depend upon Z bar. That's the whole point. Okay? But the amazing thing is, the real and imaginary parts of any analytic function in the domain of analyticity are harmonic. So I'm going to call the real part chi plus and the imaginary part w plus, and w plus is exactly my w plus. Okay? So what I'm doing is I'm introducing the analytic function of z, whose imaginary part is my w plus of interest. Of course, it's a multi-phase school, so I've got to do it for both. Everyone happy? Now here's what I'm going to do. This is my ansatz. Suppose near z is equal to 0, h plus looks like some complex constant times z to the lambda plus complex conjugate of that constant times z lambda bar, where a plus and lambda are just complex numbers. And similarly, I'm going to do an a minus z to the lambda plus a minus bar z to the lambda bar. Okay? At the moment, I don't know what a plus, a minus, or even lambda are. I put z to the lambda, and then I put the conjugate with z to the lambda bar. Don't forget, I've only put z's there because it's got to be analytic. I can't allow any z bars. But why do you think I've made that constant the complex conjugate of that one and taken lambda and lambda bar? I mean, why didn't I set this to be b plus some other? Can you see why? Well, suppose I'm on here, the positive real axis, where z bar is the same as z. Then when I'm on here, look, that can be rewritten as z bar, which means that this thing is the complex conjugate of that thing, which means that I'm adding a complex number to its complex conjugate. That means it's going to be purely real, which means w plus will be 0. Because that's the imaginary part. Everybody see? Same here. That's why I've taken that not to be a general b minus, but a minus bar. Because on here, I want this and this to be 0. So constants chosen so that no slip condition satisfied. Let's move to the interface. I've enforced no slip. So everybody pay attention. This is why I'm doing this using complex analysis. Suppose I come onto the interface from above. What's the argument of z tending to? The argument of z is 0 here. And I go up through plus fluid. And I want to come down to find the limit of w from the plus side. What does the argument tend to? Pi. Excellent. However, suppose I come down through minus fluid and go up so that I evaluate w minus. What's my argument of z tending to? Minus pi. Okay, So now I can enforce my interface conditions. So remember, oh, by the way, there's one more step. So we need continuity of velocity. And we also need, damn it, this complicated condition. The continuity of the shear stress. Now, how many people have heard of the Cauchy-Riemann equations? Well, everybody who said they did a course on complex analysis should be putting their hands up now. Yeah, yes. So, can anybody remind me what's the Cauchy-Riemann equations for this complex potential? Anybody remember? Yes.
With regards to y, I can remember the notations. With regard to y equals derivative of w plus with regard to x.
Yeah. I'm going to put you out of your, I'm going to put you out of your misery. It's this.
Okay, so
But there's two of the damn things. There's d chi plus by dy, then you put the minus sign in there. Okay? Those are the Cauchy-Riemann equations. Guess what those say in a different calculus language? They say this function does not depend upon z bar. That's another way of saying that. So that's why I always tell my students an analytic function is nothing other than a function just of z, and it's not allowed to be a function of z bar. Just like in wave problems, you're allowed right travelling waves and left travelling waves. Analyticity is you're only allowed right travelling waves. X minus ct. You can't have x plus ct. By the way, that analogy is exactly analyticity and anti-analyticity. Right and left travelling waves. I'd like to use, which one? This one, look. Because this is a harmonic function, so these satisfy these equations. So I'm going to write it like this. That's a minus. X. I'm using Cauchy-Riemann to rewrite these dw by dy derivatives into d chi by dx derivatives. Can anybody see why I've done that? Well, remember, all of my interfaces are lying along the x-axis, which means that if this is true along the x-axis, I can integrate it up along the x-axis. Okay? So integrate, I get that mu plus chi plus is equal to mu minus chi minus. And by the way, there's a degree of freedom to an additive freedom here in the constant, so I don't need an integration constant there. Okay? So you can see, look, I can rewrite this using my viscosity contrast, sigma. So I've got this and this. On the interface. Everyone happy? Nearly done. I'm nearly done. I've got a few things to write down now, so bear with me. Let's do the first one, and let's remember our ansat. Oh, you can't see it. So I think I should be able to do this. Look, I'm going to substitute these into here and here. So W plus is equal to W minus. Am I doing that one first? Actually, I'm going to do the other one first. Okay. Watch me, everybody. This is the real part of W of H plus is equal to sigma times the real part of H minus. Remember, when you take the real part of something, you take it, you add its complex conjugate, and divide by 2. But I'm going to do that on both sides, so I'm going to forget the divide by 2's. So look what I'm going to do. I'm going to substitute that. So I'm going to do A plus Z. Oh, okay, you need to pay attention. I'm on the plus. So guess what? I'm going to write Z in polar form. It's going to be radius R times e to the plus I pi. Because I'm coming from the top. I mean plus. So I'm going to write that as e to the I pi lambda. All I've done is I've substituted R e to the I pi in there. And of course, you can see what the next one is. That's just H plus. I need to add its complex conjugate. Let me add its complex conjugate. Everybody see? I've just added its complex conjugate. And now I've got to do the same for H minus, except what's going to be the key difference? Z is R e to the minus. Yeah. So I've got what? Let me just write this down here then. I've got A minus R e to the minus I pi lambda plus A minus bar e to the lambda bar. And then I have to add its complex conjugate. Here's the other condition. I'm just going to write this down. It's the same thing, just, you know, without the sigma, and you take a minus sign now because it's the imaginary part. So I'm just going to write this down. I'm going to start again. That's Z. That's Z. I'm going to subtract its complex conjugate. And then this is going to be equal to the same thing, but with a minus I pi, because I'm on a minus phase. Take away its complex conjugate. Don't panic, I just had to do that. All I was doing is I was using H plus, this was H plus, this was its complex conjugate. When I'm on the plus, this is complex conjugate, and then this is the thing where I've got the minus there. Now you'll notice on both sides, what do I have? I have R's to the lambdas and R's to the lambda bars. R to lambda bar, R to... So look, I'm going to equate coefficients of R to the lambda. There's one there. There's one there. There's one there. And there's one there. And the other equations will just give me the complex conjugate. Okay? So I'm just going to write those down. So equate. I'm just going to tell you what they are. You get the following. And you can check these for yourself. And then order R to the lambda bar gives me, oh no, this is the same thing, right? Just equating powers of r to the lambda. Anybody see another way to write those? Notice there's a common A plus and there's a common sigma A minus there. What multiplies the A plus? Cos. So look, another way of writing this, by the way, is A plus 2A cos pi lambda. What's on the right? Jack. Same thing?
Yeah.
Can you do the second one for me?
Sine, I think.
Very good. Otherwise, written as follows.
Isn't the second one minus? Minus?
Yes.
Oh, yeah. Yeah, you're right. Minus, yeah. Thank you, Demetrius, because that would have messed up the next bit. Those are what I get if I impose the interface conditions and no slip in the right rays. So what do we learn? By the way, I'm taking my time with this because, as I said, this is the kind of thing that people don't do. Well, how can we need to solve these equations. So how can we do it? Well, one choice is to take A plus equal to A minus equal to 0. Well, that means there's no flow. Any other choices? There's two other choices. A plus equals sigma A minus? Yes. That will solve the first one. Yeah, but I can only do one of those. Do everyone see? I can, he's well done. He wants to set this to be 0. So A plus is sigma A minus. And we're assuming sigma is not 1. That's the whole point of multiphase. So that's killed this one. But I need to satisfy both of these.
Lambda.
What?
No?
Go. What did you say?
Just make it so the sine by lambda is given.
Yeah. So let's do either sine pi lambda is equal to 0 and A plus is equal to sigma A minus, or option 2, well, you know what option 2 is, I do the other thing. I do cos pi lambda is 0 and A plus is minus A minus. What does this tell us about lambda? Huh? Well, don't I need pi